In olden times, people did not have technology with them. The only tool they had for observation of the space was their naked eyes. With the help of their naked eyes, they used to observe space and come up with certain conclusions. And believe me, some of the conclusions they made were not correct. One such conclusion was, they thought everything in the universe revolves around the earth, which is not the case. Then there was a person named as Nicholas Copernicus. Nicholas Copernicus said, no, everything revolves around the sun. And whenever anything revolves around the sun, it revolves around in circular orbit. And when they move in a circular orbit, they always move with constant velocity. But then there was another person named as Johannes Kepler. Johannes Kepler said, yes, everything revolves around the sun, but the fact you said that they move in a circular orbit with constant velocity is not correct. How did Kepler come to know that everything does not revolve in a circular orbit and with no constant velocity? For this to understand, we need to understand Kepler's laws of planetary motion. Let us see Kepler's first law. So first of all, we need to understand that Kepler was a very, very good observer. He used to observe planets in the sky and he used to plot them in a diagram. He used to make a diagram for it. Let's see what he did for the first law. He kept sun as the source. He kept sun as the point of reference. So for the point of reference, after keeping sun, he was observing a planet. Let's say he was observing a planet and he was observing the movement of the planet for one entire day. So during the first observation, he concluded or he came to know that it covered a certain amount of distance. In the second one day, the same planet covered some other distance. And in the third, some other distance. And in the fourth observation, the distance was continuously changing. He started plotting all the points. And after plotting all the points, when he joined all the points, he was surprised that the path was not a circular path, that path was an elliptical path. That is where he came to a conclusion that the orbit of a planet is an ellipse with sun at one of the foci. A circle has one center, but an ellipse has two centers, or we can say two foci. So sun will be at any one of the foci. It will not change its position. It will always remain at any one of the foci. So this is the first law, that is the orbit of a planet is an ellipse with sun at one of the foci. Using his first law, he had the diagram in front of him. Using the first law, he postulated the second law. How did he do that? He knew that whenever we have a planet at any point, and if we draw a straight line from the sun towards the planet, so we have this straight line joining the planet and the sun. So remember this, a straight line joining the planet and the sun. When this planet moves from point F to point E, obviously this straight line will also sweep certain amount of area. Similarly, from point D to point C, it will also sweep certain amount of area, and also from points B to A, it will cover or sweep certain amount of area. Now we can see we have these three figures right here. We can say they are sectors, or in simple terms, we can say they are triangles. Now, as of now, if you see these three triangles, you cannot see any similarity. But let me tell you, all these three triangles are equal in their area. You would be surprised, right? That means if I were to take any one of the triangle and try to accommodate in the second triangle, we would be easily able to accommodate the entire triangle. That means the area of all the three triangles is the same. That means he came to a conclusion that the straight line joining the planet and the sun sweeps equal areas in equal intervals of time. We can see that the time interval is 1 day. So this is the second law, which says the straight line joining the planet and the sun sweeps equal areas in equal intervals of time. So this is second law. Moving on to the third law. For third law, what he did was, he again took sun as the reference and he took other two planets. Let's say, for example, we have Mercury and Venus. Now we know that from the distance, we know from the center there will be a certain amount of distance. We will denote that distance with small letter r. So what is r? It is not the distance but the mean distance, because we know the orbit is not circular, it is an elliptical orbit. So right now we are taking r as the mean distance of the planet from the sun. You will have to remember this, by heart this, mean distance of the planet from the sun. Just remember this, mean distance of the planet from the sun. Now when this planet moves or revolves, it will take certain amount of time. Let the time be capital T. You have to remember that capital T is the period of revolution around the sun. So remember these two things. Third law will be absolutely easy. Mean distance of the planet from the sun. And what is capital T? Period of revolution around the sun. Just remember this, and you know that 90% of the third law is already remembered. Now, we know that this second planet will have a greater mean distance than the first. And obviously when it moves or it revolves, it will also take more time as compared to the first one. That means as the value of r increases, the value of t also increases. So if one physical quantity increases and the other also increases, obviously they are directly proportional to each other. That means r is directly proportional to capital T. Now if r is proportional to t, we can say that t is proportional to r. But there was something he noticed. Since t is proportional to r, he did not find this. The calculations that he obtained was slightly different, and he came with the conclusion that t is not proportional to r. T square is proportional to r cube. So t square is proportional to r cube is the expression for Kepler's third law. Now we know we need to remove the proportionality sign and put a constant of proportionality. So we put k as the constant of proportionality. So we obtain t square is equal to kr cube. Now what we'll do is we'll put r cube in the denominator. So we write t square upon r cube is equal to k. So this becomes the formula for Kepler's third law. So this is the formula for Kepler's third law. Now we'll write the statement of Kepler's third law. For that we have to remember t square is proportional to r cube. So if t square is proportional to r cube, as discussed earlier, we know that t is period of revolution around the sun and r is the mean distance of the planet from the sun, and we have square and r cube. So that means the square of the period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. That means Kepler's third law. We don't have to by heart it. We just have to by heart the expression. That is t square is proportional to r cube, and we know that the square of the period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. So these were the three laws. Let's revise the three laws. First is the orbit of a planet is an ellipse with sun at one of the foci. Second law states the line joining the planet and the sun sweeps equal areas in equal intervals of time. And third, the square of the period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun.